This video is about a special set of Newton's second law problems that involve more than one object, and we call those two-body problems. This is where you'll see Newton's third law coming into play because of equal and opposite reactions between two objects. So these two-body problems start off where we have, in this case, two boxes touching each other. One's 5 kilograms, one's 10 kilograms. We're applying a force of 45 newtons to the smaller box, and we're accelerating both boxes across the floor. Now we're going to say there's no friction, because that'll come later, and we also want to find the acceleration of the boxes and the force acting between the boxes. So to make all this work, we have to draw free body diagrams for the individual items. So we're going to draw one here for the small box, which is 5 kilograms, and we know that it has gravity and normal force. We are applying a force to it. Now, they're talking about this force between the boxes, and I'm going to call this a contact force. So I'm just going to call it force C, but it's the force between the boxes, and the force on the blue box is pushing back at it as you push it to the right is the contact force between the blue box and the yellow box. Now, since we're on a horizontal surface, gravity and normal force are the same. Our mass is 5, G is 9.8. 5 times 9.8 is 49 newtons, which is also the same as our normal force. Where we have a net force is in the horizontal, where the force applied is going positively and our contact force is going negatively, and that equals mass times acceleration. Our force applied is 45 newtons, and our contact force is what we're trying to solve for. And that's equal to the mass of our box, in this case the 5 kilogram box, times acceleration. This equation, we have two unknowns, and this happens from time to time in two-body diagrams, but we can use the simple tricks in algebra to get this thing to work for us. So we have one equation. Now let's draw an equation for the yellow box. Now we know the yellow box also has gravity and normal force acting on it. We know that the force of gravity is mg, and so we know we have a 10 kilograms times 9.8 equals a 98 Newton box. Our normal force is also going to be 98 newtons because we're on a horizontal surface. Now, there's nothing being applied to this, but we do have a contact force, okay? And since the contact force on the blue is going to the left, it's going to be equal and opposite. So it's going to be going to the right on our yellow box, all right? And so we got a contact force. Now, since it's equal and opposite, we know it's going to be the same number, all right? So the magnitude's going to be the same, just different direction. Now, our net force in the horizontal is just our contact force. So force contact is equal to ma. Force contact is going to be equal to the mass of our yellow box, which is 10, times acceleration. Now here's what I got. I got Fc equals 10a, and I got 45 minus Fc equals 5a. I can substitute this, right, in right here. And so I can say 45 minus 10a equals 5a. Okay? Add 10a to each side. 45 equals 15a. Divide both sides by 15. A is equal to 3. And so our acceleration is 3 meters per second squared. To find our contact force, I just take 3 and substitute in for A in this equation right here. 3 times A is 30, so our contact force is 30 newtons. So I've solved for all the forces and our acceleration in this context. Again, free body diagram for both. Sometimes you're going to get two equations, two unknowns. It's just substitution. Okay, here's another example of a two-body diagram where you have two boxes attached by a rope, and then you have another rope attached to one box, and you're pulling that rope. So we have a 7 kilogram box attached to a 3 kilogram box attached by one rope. The 7 kilogram box is pulled by rope 2 with the force of 25 newtons. We want to find the acceleration and the tension in rope 1. We know the tension in rope 2 is going to be the 25 newtons because as we pull it, that's the force we're putting on it. And tension is the same throughout the rope, so nothing's going to change there. So again, let's break it up. I'm going to draw a free body diagram here for the green box, the 3 kilogram box. We got force of gravity and normal force, and then I got force of tension for one rope. Okay. Force of gravity and normal force are the same, which is m times g. So if I took the mass of this box, which is 3 times 9.8, I get 29.4. And that's going to be also the same as my normal force. So I know normal force and gravity, but my main goal here is force tension. Now there's only one force that's acting unbalanced, and that's the force of tension. So that's going to be my only net force, and that's going to be equal to the mass of this box, which is 3, times my acceleration. So again, Ft1 is equal to 3a. So now let's draw a free body diagram for our bigger box. Our 7 kilogram box, again, we got gravity and normal force, which is just going to be 7 times 9.8, which is 68.6 newtons for both normal and gravitational force. Now this box has 2 different forces. We have the force of tension from rope 2 and the force of tension from rope 1, because here's rope 1 and here's rope 2. Since we know we're going to accelerate this way, right? Force of tension 2 will be positive, force of tension 1 will be negative. So net force equals ma. Force of tension 2 minus force of tension 1 will equal ma, my mass is 7a. My force of tension 2 we know is 25 newtons. My force of tension 1 is 3a, so I'm going to put 3a in here, equals 7a. Add 3a to both sides. 25.0 is equal to 10a. And then sorry, had to pause there. So 25 is equal to 10a. If I divide both sides by 10, right, my acceleration is 2.5 meters per second squared. Then if I go ahead and substitute that back in for T1, right, so 3 times 2.5 is 6, 7.5 newtons. So I know the tension in 1 is 7.5 newtons. Again, 2-body diagram or 2-body problem. Make free body diagrams for each and then solve, substituting one into the other sometimes. The last one we're going to look at an elevator type problem where the two boxes are held together by a strong wire and attached to the ceiling of an elevator by a second wire. The mass of the top box is 14.2 kilograms and the mass of the bottom box is 10.4. The elevator is accelerating upwards at 2.48 meters per second squared. Assume the wire has no mass, okay? That's just to make our life easy. So A, we want to find the tension here, and then we want to find the tension here. So we're going to call this tension 1 and call this tension 2. So let's draw both boxes. We'll draw the top box first, all right? So the top box has force of tension 1, and it has the force of tension 2, and it also has its own weight to worry about, right? Because it's also pulling down. So there's 2 boxes pulling down on the force of tension 1. So I look at this, and the force of gravity is just mass times g. And so the force of gravity for this box is going to be 14.2 times 9.8, and 14.2 times 9.8 is equal to 139.2 newtons. Okay, so the force of gravity is 139.2. So as we draw the force net equal to ma, here's what we know. We know that force of tension 1 minus force of tension 2 minus the force of gravity, 139.2 newtons, is equal to the mass of the top box, which is 14.2 times A. Now we know what A is. A is 2.84, so if I substitute 2.84 into there, I get 40.3. And then I go force of tension 1 minus force of tension 2 minus 139.2 will get me 40.3. So now let's look at our second box. Our second box has just two things acting on it. The force of tension 2, which is the same for both boxes, times the force of gravity. Force of gravity is mass times g, so the mass of our bottom box is 10.4. And we multiply that by 9.8. And 10.4 times 9.8 is 101.92 newtons. So I know that the net force is going to be force of tension 2 minus the force of gravity. Force of tension 2 minus 101.92 is going to equal MA, which is the mass of my bottom block, which is 10.4 times my acceleration of 2.84. I'm making a mess of this. But 10.4 times 2.84. So force of tension 2 minus 101.92 equals 10.4 times 2.84, which is 29.54. Add 101.92 to each side. My force of tension 2 is equal to 131.5 newtons. So the tension here is 131.5 newtons. I substitute that into here, and force of tension 1 minus force of tension minus force of 2 minus 139.2 gives me 270.7 newtons, and that's going to be equal to 40.3. I add 270.7 to each side, and the force of tension 1 is now equal to 311 newtons. So this is 311, while the bottom tension is 131.5. A lot hard to follow. If you want me to do this problem for you, just bring it to me and I can show it to you again. If you see a problem similar to this with two bodies in tension, just understand that the tension on this string, right, and this first one is dependent upon both masses. While for this string, it's just dependent on the bottom mass. This gets to be more difficult stuff, but not impossible to do.